10th. It's our 17th class, and we are starting a topic called linear regression today with a quick review of equations of lines. And this is a supplemental section, so you won't find linear regression in your textbook, but we are still covering sections 2, 3, and 4, so your homework from your textbook will be focused on slope in equations of lines. The take-home test is being distributed today. It's due on Monday. Please note that there's a small typo in your schedule right here for next Friday. It's not March 19th, it's March 17th. And that's when your project is due. Okay, any questions on the upcoming schedule? We're going to finish everything we need for the next test next week. By Friday, we'll have all the new information done. And when we come back from vacation, the first day will be a review, assuming we don't have another snow day between now and then, which I guess we shouldn't assume anything. And then Wednesday you get back will be the actual second test. Any questions on the schedule between now and after vacation? All right, so let's take a look at today's material. So we're going to start with this example here that this is all new material. So even if you had this class last semester, this isn't the same problem we were using. I just changed all the notes recently. So, and someone want to read this for us, Phelan? Just number one, yeah. Okay, and this is from the U.S. Department of Energy. So these are real, this is real data. This isn't just made up, okay? So often, and this again is just a quick review of lines. Often you're given either 2 points on a line if you're just looking at like a situation where there's not a context. But today we're going to be looking at situations where we have real data. So if we measured time in years since 1995, how can we take this sentence and translate it into 2 ordered pairs? How can we take the information in that sentence and translate it into 2 ordered pairs? Can anybody give me 1 ordered pair? Laurencio?
0, 206,000.
Yep. So that date, 1995, translates to x equals 0 because it says the number of years after 1995. And this is the number of AFVs. So as a, by now it's kind of intuitive that when you look at something like that, you automatically say that the time, in this case, the number of years after 1995, is your independent variable. That's what takes the place of x. And the number of AFVs here is what takes the place of what we normally call y. Okay, so what's the other point? Can you help me with the other point, Jesse? Okay, it's 1997, so 2, right. 2, 280,205, right. So just real quickly, if we were to plot those, right, just to have a little idea of what's going on, we know that the independent variable is the number of years after 1995 along your horizontal axis. Here are the number of AFVs. And the first point is what we typically call our y-intercept. And our second point is up here somewhere. And so what we're going to be doing now is finding the equation of the line that joins those 2 points, off of which those points are a solution. Okay, same to the equation. So to find the slope, what do we remember about the slope? M is the letter we use. Anybody remember how to find the slope? Okay, y2 take away y1 divided by x2 minus x1. Shortcut that, you can use the Greek letter delta, that little triangle, to say change in your y variable over change in your x variable. Note it's a rate. The slope is a rate of change between 2 variables. In fact, it's a constant rate of change. All right, so it doesn't matter which of these points you call x1, y1, or x2, y2. So I'm just going to go in the order that they were given. And so we have 280, 205, take away 246, 855, divided by 2, take away 0. Notice I put it in parentheses because what I like to do now, and this is to help you because you'll be seeing these types of questions in your projects and in your quizzes and in your next test. It is interpreting what slope means. We're past the point of just calculating these meaningless slopes all the time. Everything we do now will have a context. It will be dealing with raw data. So I like to put right up here the actual units right after the number. And that's going to help me with the next part where it says interpret what the slope means. So this comes out to be 16,675 AFVs per 1 year. So we usually just say each year or per year. So now that you see the slope with the units, your interpretation of this rate of change in the context of the story, you can just read it right off of Part B. You can see what the slope means. Anybody want to try to put that into a sentence for us? Every year after 1995, the number of AFVs in the US increase by 16,675. Perfect. Okay. So there's lots of ways to write that sentence. Nora? Because I simplified this. I took this number divided by 2, and then I simplified, because if you look at this, this is going to be 32,000 something over 2. So I've reduced the fraction to, yeah, right. So this is 33,000 something over 2, and I just reduced it down as far as I could because often we want to, it doesn't matter, but in this case, we often like to talk about our slopes as per 1 unit. It's called a unit rate. Like, right, when you go out to buy your gasoline, you don't want to see what it is for every 3 gallons of gasoline. You want to see what it is for every 1 gallon. That's called a unit rate. So often, it's not necessary, but often we write our slopes as a unit, right, with one in the denominator. So yeah, I skipped a step because I couldn't remember what those numbers were subtracted, but I remembered what it was reduced. Thank you for asking. All right, now find the slope-intercept form of a line. This is one of the forms of a linear equation. There's 3 forms that you're going to work with throughout section 2.3 and 2.4, and you'll have exposure to that in your class activities today. This is the one that people can usually repeat like you're a choir. You know, you come out of high school and you think this is the only form of a line. So in this case, we want, we know what the slope is. It's right here. And so it's 16,675 times x plus b, whereas b is your y-intercept or your vertical intercept, whatever happens to be the variable on your vertical axis. So in this case, we lucked out because one of our points was the y-intercept, so we don't have to do any more work. We can come up very quickly with our equation because we're given all the information we know. So this would be the equation for the line that goes through those 2 points, those 2 pieces of real data. Any questions on that? Add what together?
No.
Okay. All right. Any other questions? All right. Explain the significance of the y-intercept in the context of this particular problem. So our y-intercept is 0,246855. So Evan gave us the last sentence, part C. Who wants to tell us what the y-intercept means? James? In 1995, yep. Yep, perfect. So in 1995, because 0 represents the number of years after 1995, so that's our beginning point, 1995, and that tells us the number of AFVs in the US. Any questions on that? Now note, again, this was part of your first project you did. Both the numbers, 1995 correlates to the 0. The fact that it's a year corresponds to the unit. This number is in that ordered pair and the units. So remember, you need both numbers and both units when you write your sentence to interpret it. So I can read the sentence and then I know a lot about the data. Okay. Use your slope-intercept equation to estimate the number of AFVs on the road in 2003. Okay, so this is a situation where you're given your input value and I'm asking you to find your output value. So you take your equation, y equals 16675x plus 246855, and you say, all right, I already know what my input value is, so I just replace my variable x with that number. So I've just got to figure out what's the value for x here. 8. I don't put 2003 in because x is the number of years after 1995. So I subtract and I get 8. So to figure this out, I would simply put in an 8 for x, and I would come up with an answer. Thank you. 382, 350. Okay, 380, 255. Good. The actual number of AFVs on the road in 2003 was 510,805. So have we underestimated or overestimated just knowing those first 2 points? Totally underestimated, right? And by how much did we underestimate? Those of you who are out there quick with your calculators. Maybe not so quick. 510,805 minus 380,255. 135.50. Is that right? Okay. So what does that tell us? What this tells us is by just taking these first 2 years, the data for the first 2 years, knowing that there's going to be real data for years beyond 1997, this is not a really good equation. It seems to be growing much quicker than this equation would predict. This equation is only predicting that there would be what? 380,255 AFVs when we know there's well over 500,000. Okay, so we'll see what happens to this in a few minutes. So now we're still asking this question, what year were there 510 AFVs, 510K on the road? So now we're given the input, we're given the output, and I'm asking you to find the input. So here we're asking you to solve for x. So it's important that you recognize which of these numbers go where in the equation. So that is your output value, that's y. And now you're going to solve this equation for x. Okay, and I'm sure everybody can do that, so I'm just going to move along. Okay, so let's take a look at the rest of what we're really going to do today, which may be new to many of you. It's called linear regression, and we're going to continue to work with this story about the number of AFVs in the US. So if the number of AFVs increased each year by 16,675 vehicles, then the scatter plot would look like this. Notice each year from 1995 up to, what is that number there, 2004, we would have this many vehicles, increasing by exactly 16,675 per year. So that would show the slope. As each year goes by, we go up by 16,675. And this would not change between any of the 2 points on this particular graph. Right, so that's what it would mean, and these would be the values based on the line we created just using the first 2 data points. Okay? So this earlier equation we found would pass through every single point exactly. And we call that perfect correlation when the line passes through every single data point. But let's face it, when we model real-world variables, we often will get a scatter plot that looks more like this. They don't fall in an exact straight line, whether the straight line is moving in a positive direction or whether it's moving in a negative direction, okay, a negative slope or a positive slope. But they do show a tendency or a trend to be increasing in a linear-like manner, don't they? We see that as we move from left to right, as the years increase, our number of AFVs are increasing, and it's not exactly by the same number every year, but they look pretty much like you could kind of draw a straight line through there. So I don't want you to worry that we can, even though it's not a straight line, we're going to be able to find an approximate linear model. And this is what I want to keep pointing out to you. We're going to create a model. So all the information we get from this model will be estimates or predictions. So again, if you think back to project 1, those of you who wrote estimates and predictions, you got full credit, and those of you who forgot it. So I want to keep emphasizing, we have the real data right here. So our model is not going to predict it exactly. And then if things continued like this, maybe we'll get a pretty good estimate. But maybe after this, they started to decrease, or maybe they increased so much greater that the line isn't going to be a good predictor. We don't know. So let's take a look at number 5. So here's our real world data with a line drawn through it based on the very first line we got from the points 1995 and 1997. So look what happened. If this is a line with the slope of 16,675 going through that 0.0246855, notice it would be a really good predictor for the first 1, 2, 3, 4 years. Not too bad, right? Out to here. But what happened in our class demo when we asked for year 8, the year 2003? We were down, right? A lot. Does anybody remember what it was? How far underestimated we were? Yeah, more what? Yeah, 130,000. So where's year 8? Here's 1, 2, 3, 4, 5, 6, 7, 8. I is year 8. Look at how far below. This is your predicted number of AFVs in the year 8 years after, or 2003. Look at that huge gap. It doesn't even look as big as it actually is on here, because look at how the scale is going up by 100,000. But if I made that scale even less than a jump, every jump is 100,000. So that's more than 100,000, because each one of these spaces represent 100,000 vehicles. So this is why we talked about earlier in class 2 that, hey, this model's great for the first 5 years, but then look what happens. That's why going too far outside your data range can be really tricky. So that model was good for 1995, 96, 97, 98, and 99, but then it really is going to underestimate. So what I'd like you to do now, I'd like you to choose any other points, or maybe not choose any points at all, and take these rulers, and at your desk, I'd like you to draw your own line through that data set, through that scatter plot. You draw one line that you think gets as close to all that data as possible. Okay, so you'll all have different lines. There's no right or wrong answer here. Okay, just eyeball it. So you've got one line there already that you see doesn't work too well for all the data. So if I could perform magic and come out there and get all of your lines and quickly superimpose them on this scatter plot, I might get something that looks like this. Yeah, I might get something that looks like this. All right. So this semester, we're going to let our calculator, the one that's at your desks, or you can use GeoGebra. It's actually very quick with GeoGebra as well, to actually find the line of what we call the line of best fit. Because I don't know which one to select. If I started looking at these, I'd say, oh, that line looks pretty good, but I don't know, maybe this line is better. You know, this can't be like just an arbitrary thing. We want to know what line fits that data the best. And there's all these mathematical calculations your little calculator is doing, which saves you an enormous amount of time. Back in the dark ages when I was taking stats in college, I had to find the line of best fit by hand. Okay, we didn't have personal computers then, we didn't have these fancy calculators. So please don't complain to me because you might have to press 3 buttons, okay? Okay. You may have to press 4, right? Okay, so I put this data into the calculator. I'm going to show you in a second what some of the steps are, but I'm going to do that individually with you. The first thing that you're going to do is you have to enter this data into your calculator. So if I just pick up my TI-83 Plus, don't even bother doing this right now because everything's written down for you and you're going to be doing it in about 5 minutes. So the very first thing you have to do is enter the data, or you have to edit your data list. So I just hit enter. And you see L1 and L2 here. So you literally, and you won't be entering all this data. This is way too many numbers to ask you to punch in today. It would take you too long. But you would put 0 and hit enter, and then 1 and hit enter, blah, 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 all the way down to 9. And then you'd go over and you'd hit 2, 4, 6, 8, 5, 5, and hit enter, and then you'd come down and you'd do your next. Now, those would be your list. I'm just going to do, actually, let me change this and do the variables that we initially found the line through, right? Those were our first 2 points. So 2 is, I don't have my glasses on. Can anybody read that for me? 2 what? What was the original point? Yeah, 205. Okay. So let's suppose I just had those 2 data points, right? And instead of all 10 of them. Then I'm going to go and ask the calculator. I use my stat button, but let's suppose I had 10 points there and I want to see the plot of all those points, the scatter plot. Well, I would go second y equals, because right above the y equals it says stat plot. And I'm going to come down and I'm going to first turn on my stat plot. I'm going to turn it on. This first graph is highlighted usually for you. That's the scatter plot. And then these are your 2 lists of data, L1 and L2, and this is the little mark you're going to use. For any statistics plot, you hit zoom 9. Remember we talked about earlier in the year zoom 6 being the standard window that went from -10 to 10 on the x-axis and -10 to 10 on the y. Well, zoom 9 will create a scatter plot of your data. It's not very interesting because it's only 2 points. Here's your y-intercept and here's your other data. But imagine having the scatter plot I've already drawn for you on your class notes, right? Then to actually get the line of best fit, I go over to calculate and I go down to linear regression. Notice there's another linear regression line and people say, why do they have this? It's really interesting. Algebra class used this because this looks like mx plus b. Stats class always used it with your starting point. To me, it always seemed backwards that we would have mx plus b instead of saying, here's where we're starting and we're either increasing at this rate or decreasing at this rate. So actually the stat version of the equation makes more sense to me, but we'll stick with the algebra version. So you hit that. And this now is the old calculator. If you have the yellow, the steps will be different. And the steps are all listed in your notes. I'm just showing you how you would do it with the black 83 plus. So I have to tell it, where's my data hiding? My data is hiding in L1 and L2. And if you notice right above the keys 1 and 2, the little yellow L1 and L2. So I hit second L1, second L2. Oh, I forgot my comma. Add. So I got to delete that. Put in my comma, which is right here. Second L2, and I got to put a comma. Now this is probably the one that students forget. And it's okay. If you don't do it a million times, you're going to forget how to do the steps. You have to now tell it to store the equation, the line of best fit, in here into your y equals, either y1, y2, y3. So you're just going to tell the calculator where to store the equation. To do that, you have to hit this vars button right here. And notice it has vars and then it has y variables. That's what vars stands for. So you just cursor over and say, okay, enter. I want to put it in one of these y1, y2, y3. You pick one. We usually put it right in y1. And now it's all set to calculate. So I hit enter. Now there's my equation for my line. A is the slope, exactly what we got a few minutes ago, 16,675. B is my y-intercept, and there's my correlation coefficient. It's an exact fit because I only have 2 points, so anything's going to have a correlation of 1. So those are the steps you'll go through with some real data, and I'll help you go through all of that when you get to question 2. All right, so let's take a look at the final piece, which we just ran into, called R. It's called the correlation coefficient. That's the last thing we have to cover. So if we look at a scatter plot and it looks like a line would be a good model, we can't really just rely on our judgment. There's a way that graphing and using different scales can sort of fool us a little bit. So we want to find a statistic that quantifies the strength of that linear relationship between the variables. And that statistic is called the correlation coefficient, and it measures the strength of the linear relationship in the direction, because as we know, we can have a line that has a positive slope or a negative slope. So if you wanted an exact fit, it would be these first 2 pictures where all your points line up in an exact straight line, which is not anything you're going to find in the real world, but you find things very close to an exact fit. If it's in the positive direction, which means as x increases, y increases, then your correlation is 1, exactly 1. That's the strongest you can get, and that's in a positive trend. Similarly, you could have a negative 1, where all your lines fall in an exact straight line, and as x increases, your y is decreasing. That's a negative 1 slope. So anything close to negative 1 and positive 1 is a strong linear association. If you have a bunch of, you look at your scatter plot and there's a bunch of it looks like a cloud of points, there's any line could fit through there. There's no direction indicated. That means your R value is getting really close to 0. So I've given you some examples to look at here, just for your own perusal. If we looked at going from R being your correlation coefficient from being from 0.33 up to 1, you can see how these points start. It's almost as if there's a magnet in the middle here drawing them together to go from a sort of a very weak correlation to a extremely strong, meaning a perfect correlation. And here's another example again showing you, look, this one you would never ever try to fit a line to negative 0.08. It's just you would say there's no way I can find a model for this, at least a linear model. Yeah. Because these are tending, if you look at it, they're tending to move as you go left to right here, Colton. These are tending to go up. Not all of them, but that's the tendency. Whereas these, and this one it's almost close to 0. So this can almost, you could say, well, that's moving up as well as moving down. That's why the number's so low. And then again, if you were thinking about putting a magnet right in the middle and starting to get all these points coming towards the center, then you would finally get the negative 1. So remember, a strong correlation doesn't mean X causes Y. That's one of the pitfalls that people fall into. I mean, a number of steps in the years that the Attorney General went through to actually state on cigarettes that smoking causes cancer. It was an enormous study with many, many steps and many, many trials and lots of different statistics to actually say, because to ever say something causes something is an incredible statement to make. So it's not taken lightly in statistics. So here are your activities, but what I would like you to do is I want you to start with 2 and about the average concentration of carbon dioxide in the atmosphere and the average global temperature. Now, we won't send this to our EPA secretary or director because they don't believe in any of this, but we're going to just see, all I want you to do today is just learn how to put this in your calculator and come up with your line of best fit. So down here where it says equation, you could write line of best fit. Or you could say regression line. I'll get it for you in a minute. I'll get it for you in a minute. Okay. Just so that you see something other than equation. I want to point out one more thing, folks. Back here. Because I was kind of going quickly because I want you all to have time. Here's the line of best fit. Here's the actual line. Look at the slope of the line of best fit compared to the slope we got going through those first 2 data points. Look at this slope. How can you compare those 2 slopes just quickly? It's almost double what we got because ours was what, 16,675, right? So that's why that line that we got stayed well below those points because the slope was not steep enough. The other thing I want to point out, and if you could get into the habit of this, put a little hat over your Y because that will help you to remember that this is a model and it's just an estimate. You're just getting estimates out of this model. It's not your real data. Okay. All right. So turn to number 2. If you're using the yellow calculator, then when you get to the bottom of page 7, where it says 83, 84 models, if you're using the yellow, once you get there, if you're using the yellow calculator, just turn the page to where it says 83 plus and 84 plus models. So start your activities with 2, and then you can go back to 1 and then move on for your review of equations of lines. That really is just a review of 2, 3, and 2, 4.